Hello, how is everyone doing? Welcome back to the channel, and this is going to be the first video of I don't know how many, to be honest, about like things you need to know before going into interviews, things you should know mostly about drawings and tolerances and all the GDRP and all that shit, because, well, bit of a story time before we start. Yeah, so before I started like actually working as a when I was looking for a job right out of straight out of university, I ran into a few interviews where I had to like interpret a drawing, or I had to explain to the interviewer what the drawing was doing, or whatever the hell. And I noticed a lack of understanding or a lack of knowledge when it comes to tolerances, when it comes to reading a drawing, because no one really, if you look at YouTube, no one really shows you how to read a drawing, what a drawing is. At the time, I looked at different channels and I couldn't find what it is, how to use it, and the different standards. So this will be specifically for Germany, but the principles are the same. It's just that you're gonna have different, like slight differences, slight changes from country to country. If you're in America, then good luck. You're working with Imperial, but and the callouts are a bit different. But all in all, it stays relatively the same. And these are things that you can know, you should know. And if you're competing for a job right straight out of like university, this could give you an edge. Because I kind of found out that even though I'm an engineer, I do a lot of like technical drawing related activities. Also, I have to like disclaimer, I'm not a technical draftsman. I am a mechanical engineer, so I'm not like super fully up to date with all the norms and all the standards and all the things. But these are things I run to every day, and they are not complex. They are not super crazy. It's just you sort of have to know. It's good to know. It will help you if you know this. Yeah, let's start with like how to approach a drawing, how I would approach a drawing. This plate comes from the vacuum industry, like vacuum cells for different processes, and we're gonna have a bunch of specialty annotations and mostly standard, normal, regular things you're gonna see anyway. So usually we start with this view. Like you can look at this to kind of see what it's like. It's a plate, sort of rectangular. It has a bunch of holes. It has a slit in the middle. Well, not in the middle, but yeah, offset. And yeah, so what do you do? Basically, the way I would start with reading, looking, and seeing how to interpret it, or how to sort of get a feel for what it is. So we have the main principle, let's say measurements, like width, length, and here you can find the thickness. Probably should be here, to be honest, but you can find it here. And then, so yeah, it's a 30 millimeter thick plate. It's 2 meters wide, 2 meters long, half a meter wide. So it's pretty massive. At the bottom, you should be able to see that it weighs 272 kilos. Cool. Now, you have a bunch of holes here. It is best practice to put this out of like where material is, but you also don't want to like intersect two lines. So I guess this is why it was decided to put it here. So we are measuring from the middle for these holes, like horizontal and vertical. This makes the job of whoever is going to CNC it a bit easier, maybe. Sometimes you will be working at a place where you can talk to the CNC person who is manufacturing it, and he will tell you what is like better for him. Other times, you just need to fully define your part, and it's whoever is manufacturing these things problem. Like if it's a subcontractor, if it's a whatever, they need to figure it out. We have these holes at these distances from the middle. This yellow, this is why I hate SolidWorks. Yeah, this is the center line. You have holes at equal distances along the thing. You have 13 of them, and I think this is for each. Yeah, you have 13 here in this line, and then another 11. And these are 18 straight holes without the threading. And you also have this, like this is the length and the width, and it is through the whole material. It's not a slot like let's say 15 millimeters deep that you would have to write in a different way. So basically we have this plate, we have these holes, we have here 2 holes on the side. They are in section D. Section D is over here, and you have this here 2 times 30 millimeters diameter with a fit H7. I think I will do a video about fits at a later time. But yeah, this is a fit. It dictates how this hole interacts with the shaft that goes through it. That's what you need to know. For now, you can look it up, or later on look at my video. This is the position of the hole with a tolerance. So it can be a 40.05 from the bottom, or 39.95. This is the area, because no dimension is exact. You heard about it, but this is how it comes to be. This is a surface treatment. It needs to have a roughness of RZ 6.3. What it means you should know already. If not, you can go and search it, look it up. RZ and RA. So this is something you can also, you can communicate information like this. They chose to communicate, this is a drawing I worked on a very long time ago. It tells you about the cleanliness of this thing and this surface, and basically everything that is interacting with vacuum. To be honest, this doesn't need a 6.3, but the boss decided that it gets a 6.3. Yeah, so this is for the surface treatment of not the machining, like the roughness of the surface. Here you can, I detached it now, and you can put it on top of this, but usually you drag it out so you have a line. Now, what else do we have? Usually when you get a drawing, this is an A0 sheet, so it looks, in reality it's way bigger. Yeah, it's an A1. So yeah, we have the holes, we made the holes, and on the other side, so if you cut it like this, D, and then you're looking through the material, you have these holes. This is the back side. So if this is the front side and this is the back side, although it's actually, in reality, this is the back side, this is the front side. So here you have, for example, these 24 M16 holes, and they are here. So I'm guessing these. I don't actually know if that's correct. Let's see, because it was all done by hand. So yeah, 24 M16s. Yeah, hole call out later. Here you have another hole that's 50 millimeters deep, 12 in diameter. You have 2 of those, and they are H7 in the fit. This side, so if we are in the section here, DD, and the back side, so this side should be machined to RZ25, which is a roughness and definition. And you have this thing here that's 25. This can't really be, I think. Those are these, right? Yeah, anyway, there should be like a triangle here, because this hole is really hard to make. It can be made, it's just expensive. Anyway, and 25 millimeters deep, 20 millimeters for the threading. And what's missing here is like that, it's M16. It's probably the rest of these. So yeah, normally you would put this over there, and you don't need to put one dimension here, one dimension there, because it confuses people who read it later. What else? So this is the plate from the side. We are in the first angle, so this side is here now, like we are flipping it 90 degrees. So you can see that we put a datum here. This calls this. We are calling this plane A, and we are telling A that it needs to be planar up to 0.2 millimeters, meaning any 2 points on this plane should not differ from each other in height from the zero theoretical dimension by 0.2. Like it could be 0.2 upwards, 0.2 downwards, but from the zero where we are, where we define some kind of arbitrary zero, from that side we shouldn't differ by more than 0.2. It is parallel up to 0.2 millimeters to A. You have the reference here. Now, I am quite sure that this is redundant here, like it's overdefined, because if we define A as planar to 0.2 from an arbitrary zero, from the dimension we define, and then we define that this is parallel up to 0.2 millimeters to A, then this should already be there. But yeah, sometimes you would have these things that are like, if you look at them from a theoretical viewpoint, they are redundant, but sometimes it makes it easier on the people who are actually working on the piece, who are like, they are not engineers most probably, and it helps them understand what you are trying to say. The one and only reason we have drawings is to communicate what we mean. That's it. So if you can do something to be extra sure that what you mean that the other side understands it and it is fully defined and anyone who looks at it will understand, then good. That's all we need. Now, this is something you will probably not see. These like broken lines. This basically means that this area here, which is, we have it on the length, it's, so the big sides are 2090 and small sides are 1930 millimeters, and we have here the other, like the width. So we have here it's basically a projected area of where this part interacts with another part, and it needs to be machined to RZ 6.3. Now this Z needs to be small because that's how it works. It's not a big Z, it's a small Z. And another thing I want to talk about is these tolerances. You have all these like 165, 330, 495, 600, and all of them are plus minus 0.2, which is good. This is fair enough. This is correct. You want each of them to be plus minus 0.2 to the middle, not to one another. So already good. The way I would do this right now is, do we have a section of these? No, but still, you can take this. You can take this guy, and you can tell it that their position is 0.2 A, B. And then you tell this thing that it relates to that one, but then you need to also define a B surface or plane like this. So basically, let's change this to B and C. So if you have B and C, you are 0.2 millimeters in reference to each of these planes, and then you can get rid of all of these plus minus 0.2, which is not that bad. Let's tell it none. Yeah, so that would be equivalent. and then you have less crap on top of the drawing, and it doesn't look so packed with everything. So that's something you can do. There are different ways to communicate the same idea. It usually depends on the company you are working at and where you are and what they have been doing until now, even though it might not be the most correct thing. You have to know. Now, let's look at this thing. This is an M16 hole. We have two of them, one here, one there, and they are 35 millimeters deep for the drilling and then 32 millimeters deep for the threading. This is to lift this part because it's 270 kilos, so no one's gonna lift it by hand. And this is for the crane. And you have this center line, meaning this hole sits in the center, on the center, like 15 from top, 15 from the bottom. And you have 2050 millimeters between them. You will notice that it is not, like it is, let's pretend it's not fully defined. Like this is a 85 from this side, right? And now it is fully defined. And we can see that this is also 85. So basically, if you omit this and put it, you don't need to put a center line on this kind of view, but let's say put a center line in the middle, and then this is 2050 around the center. That's fair. That works. It's okay. It's legal. What else do we have? So on this, we said that this is the back side. This is the front side, right? Did we? Here we have the seal. Whatever. So let's look at C. We have F. This is F. Okay. So detail C is over here. We are enlarging this and we are putting it here. Also, you might notice that here we have 005 and here we have 02. These are two different series of holes. And yeah, I think there are two of these. And you have to pay attention to these things because you could say, oh yeah, everything is 02, but no, not everything is 02. You have 005 and 005. Weirdly enough, this hole has 005 on the horizontal and 02 on the vertical, but whatever, right now. At this point, whatever. So, C, detail C. We have here a channel. This is from the top, this is a cross section. This is a specialized vacuum, let's call it channel. It is for the seal of the vacuum. This is a rubber-based seal as opposed to a metal-based seal. And basically this describes the drill bit, the drill head. We have these dimensions that the machinist has to like, he has to be within these measurements, but they are because of the drill bit. So usually it will be like that as long as he keeps his center along this path. This path is defined here at 1540 and with the other one 265. And very important, this 180 is the middle of this, I think. Let's see. 140, 125, no. So I think this is underdefined actually. Like, yeah, you need this 55 and 265 and the length in order to be able to say where it is exactly. Like right now it's floating. It doesn't have a definite position. Right? Am I missing something? This is 70. Yeah. So basically this is missing. You see, there are problems with. You can always improve drawings. This is something that happens. Anyway, so here we have the center line, and it correlates to this center line. This thing has a depth of 6. This depth of 6 is actually this channel here, and it is there for technical reasons, let's say. Basically, it's so that air has somewhere to go, because here you have the seal, the rubber seal, and basically if you don't have these, air gets trapped here, and it's less than ideal. But yeah, that probably doesn't interest you at all, so we can continue to more things, although this video is already quite long. So we had datums, we had tolerances, we had planarity, we had here positions of holes, we had some how to call out a hole, we had a bit how to call out a hole, depths, ends of holes, we had surface treatment or surface machining, we had a bit of fits. This is it's also called a phase in English. Let's say it's a phase, it's a chamfer. Here you can define it as 5 times 45 degrees. That means the depth is 5 and this is 45 degrees. You can also do it with other angles, but I would usually define the height and length if it's not 45 degrees. Like right now it's 5 towards here and 5 towards there. Anything that's not that, I would define specifically. What else do we have here? Radius, this is 20. So for anyone who worked with like drawings, it's obvious that this is 20, this is 20, this is 20. So times 4. Also notice this defines the center line, because we don't care about this. Our channel here, this thing is defined around the center line. So we care about this. Like whoever programs the CNC machine needs to do this, needs to follow this path. We don't care about the rest. Is a derivative of this. You don't define it over the sides. So you know that these are 6 deep and they are 67.5 long here. They were 70 over there. And how wide are they? It's a very good question. I don't think it's defined. It is. It's 5. Yeah, okay, so that's fully defined. You see, this video also shows you how to, like, you need to, when you have a drawing in front of you, you need to, it's not personal, but you have to go and find, like, where did you fuck up? Where is the fuck up? Where did you forget something? Where is something missing? Because when something is missing, whoever is manufacturing this might ask you, like, hey, what did you mean here? Or they might do whatever they think. And then you get something you didn't want. You have here 4 times of, so this is 30 times 30 or 30 times 45 degrees. This is 180 from the bottom. What else? This thing, does it have, is this one defined? Yeah, here you go. This is 163 plus minus 0.2, because it is very important for this slit to not move too much in the direction of up and down. Left and right it's okay because there's enough clearance, but up and down, this interacts with another part, and which interacts with another part, which interacts with another part, and they have to be level with one another. Anyway, I will leave it at this, and I hope this helps anyone. I will do another few videos about different parts, maybe less complex, maybe more complex. I want to show a bit different ways and different types of tolerances and datums and weird things you're going to see on drawings. I'm going to show what is bad, what is good, what is smart, what is not, and so on and so on. Yeah, actually, this is super important here. So, I hate this notice. I hate this thing that they write. Attention, all dimensions are finished sizes. Please take this into account when cutting. Because, of course, I am giving a finished part. The part that, like, this thing, all these numbers are finished. I don't care. I don't care what happens. I don't care what you do. I don't care if you take 5 meters times 20 meters and you can do whatever the hell you want. I don't give a fuck. Like, I ordered this. Whatever happens to the piece, to the raw material, whatever it is, I don't care. This is like meaningless. Should be meaningless. But they wrote it because they had problems with whoever was manufacturing this. Because for some reason they decide to be dumbasses. So yeah, anyway, this concludes it. Consider liking and subscribing if you want more of this. And I will see you in some other video.